But what we're talking about today is HTTP3 and Quic.
Okay, so it's our first time meeting in real life. So
it is, yeah.
Nice to meet you.
Nice to meet you, yes. Well, there's lots to get through here. HTTP3 is obviously the third version of HTTP, but it's a lot more than just a version number change. It entered the Internet Engineering Task Force Standards Track, became a request for comments in, I think, June this year. And I think it's one of the most revolutionary things I've come across in all my time doing networking. But also, it's kind of a really disgusting hack. I want to try and explain why I think it's so really good and exciting, but also why I think it's so awful. There's a couple of things we need to understand to start. So one thing we need to understand is the network stack. And as far as networks concerned, this is real ancient history. You've got a very good video by Richard Mortier about 9 years ago. And Mort does a good job of running through the whole thing. And if you don't know what the network stack is, take a look at that. But let's do the basics, right? Let's do the real basics so we get up to date. I'm going to skimp over a lot of details here, so please do not be offended. I'm going to miss out completely several of the layers, but the layers that are important today are the application layer. That's where all of our programs live. When I'm telling our students, this is the fun one. This is the one where your computer game is. This is the one where your web browser is. This is the one with your social networks. So the application layer exists on your end computers, on the servers. That's running the software that communicates with the network. So that's our top level. And I'm going to put into the side here the transport layer. And the job of the transport layer, it sits on the end hosts. And its job is to make sure the data you get is good. And I'm going to specify that more precisely in a moment. Below that, we have the network layer. And the network layer's job, that gets the data to wherever it's supposed to be. If it's supposed to be in Berlin, Shanghai, London, wherever, the network layer's job is to carry the data the whole distance. And I'm not even going to talk about the data link and the physical layer below. This is what we're interested in today, the network layer and the transport layer. And at the network layer, there's really only one game in town. There's Internet Protocol. You can have a version 4, you can have a version 6, and there's other little bits of things associated with Internet Protocol, but most of the time, the network layer is about the Internet Protocol. The job of this network layer and the Internet Protocol, to carry the data between computers. The transport layer, we have two options: transmission control protocol and user datagram protocol. Last time we spoke, I was talking about transmission control protocol. These sit at the end computer, and they're trying to impose some kind of order on what the network layer sends to us. I'm going to circle the UDP in red because it's unreliable. If data is lost, it stays lost. If data is sent so fast that a buffer overflows and all the packets disappear, they stay disappeared. I'm going to circle TCP in green because TCP does loads of things. TCP makes sure you send the data at the right rate. Last time we were talking about congestion control and how TCP tries to get the speed of sending data correct. But TCP also makes sure the packets are retransmitted. So if a packet is lost, it's TCP's job to make sure that we get that packet back. If packets get out of order, if they overtake each other, it's TCP's job to make sure that the packets are put back into the correct order. So let's imagine TCP, it's sitting there on your laptop or on your mobile phone. It's looking at the packets it's getting from the network layer, and it's saying, is this packet garbled? Is it the next packet? Do I have to ask again for a missing packet? Is this packet in order? And only if the packet is reliable, correct, and in order is it going to be passed up to the application? Sounds great, right? So TCP is the one you want. It's going to pass you the right data in the right order with no gaps. So on top of that, let's put an application, HTTP. And most of the traffic being sent these days, it is HTTP. HTTP has been around a long time. Started in 89, first official version 1.0, I think, in 96. We didn't get to 2.0 until 2015. And HTTP 3 is June. I think it's June, might be July, but it's this year's. Here's the problem. TCP is really good at being a pipe for data. It sends bits go in one end, and they come out the other end in order. But it's agnostic to what the application is. It doesn't care. The other problem is, it's very, very hard now to change TCP and UDP. Let's have a look. Let's have another drawing. Let's try and make ourselves a little network. So here, the traditional way of drawing the internet as a big confusing cloud, and we'll have some routers or routers if you're American. So all of these X's being routers, and we get to the end, and let's have something representing a server here, and here we're going to have our laptop. And we're going to have TCP here and TCP here controlling the reliability, and everywhere else IP, IP, IP. And that's the original design. That's how it's supposed to work. And the idea was that because of this layering, let's imagine we found out that TCP didn't quite work, or we needed to modify it. We could have another one. We could put in something else. We could have Sean's TCP or Rich's TCP, and it's a different protocol, but maybe we could pop it in at the transport layer and that would be fine. But there's a big problem with that now, because actually this diagram, which is what you'd show to somebody who's learning a beginning networks course, is missing a bunch of horrible details. We need what's called middle boxes. Have you come across middle boxes?
No, well, I'm guessing what they might be, but...
A box in the middle? Yeah, we need some extra things. So people went, firstly, we started to run out of IPv4 addresses. Well, not first, but that's one thing that happened. So we need...
And then there's NAT, isn't it?
There's NAT, exactly. Network Address Translation. So we're going to pop in a NAT box here, probably a NAT box here. You might be sitting behind multiple layers of these. I think at home I'm behind at least 2 layers of NAT. Then you might want something else. So this is going to be a data center. So maybe we're going to pop in a load balancer here. So a load balancer, perhaps, well, definitely we want a firewall, right? So you can't go on the internet without a firewall. So let's have a firewall in here, and probably want a firewall at the other end as well. And maybe you've got some middle boxes sitting here as well, doing some monitoring. Here's where we start to get a problem. Because all of those middle boxes, they're meant to be very neutral. They're meant to be just passing on IP traffic, but they start to make assumptions. They start to say, we'll be in a firewall. Let's have a look at the TCP, see if there's something dodgy about the TCP connection. The NAT box goes, okay, we need to know whether this is TCP or UDP. And suddenly, you've got a problem. Because if you design something that's not TCP, it's going to break all these middle boxes. Or rather, it's not going to break the middle boxes. The middle box is just going to go, that's garbage. Sean TCP is a definite no-go. We're throwing that packet in the bin. It's not properly formatted TCP. Maybe somebody's hacking. Or it's just not going to understand it or know what to do with it. So we get the problem that we call ossification. We're stuck, we're frozen. I think it comes from bones, actually. But anyway, you're kind of, you can't change any of these things. You can't have a UDP or TCP that changes anything that's going to be sent over the network, because these middle boxes are a problem. Why do we want to change them? Well, I said TCP was good at being a pipe for data. But if you know what that data is, you can make some optimizations. If you knew your data was HTTP, there's a lot of things you can do. So let's look at one of those things. I think I mentioned before TLS. You've got a very good video with Mike Pound explaining that. So when TCP starts off, it needs to do what we call a handshake. So we need to kind of introduce ourselves to the server, make sure that we've got a connection. And this is something you teach in every basic networking class, and I'm sure most of you know it already, or many of you do. So we have a client here, and we have a server here, and so time is coming down in this direction, and each of these lines is a single packet being sent. So the client wants to connect to the server. It's going to send an SYN, a SYN packet. The server is going to respond with a second packet, a SYN ACK. The client gives an ACK, and that's the first time the client can send data. But these days, we also want security. We want HTTPS. It's no good sending things in plain text. So the client's also now going to request a security. It's going to use TLS. In HTTP2, we'd have TLS 1.2. It's going to send a hello. The server's going to send back a certificate. And now we've added on exchanges of data. That's very important because a web page is a complex old beast. There's lots of things, even on a fairly basic web page, you've got some HTML, you might have a little bit of JavaScript, you've got some images, you've got a style sheet. That web page, even if it's fairly simple, is going to be several files. And if you're looking at a really complex web page, dozens of files. And this client and server may be geographically distant. So each time you do there to there, you're adding a round trip time of delay. I'm sure you can see right now, looking at that, there's something kind of obvious you could do.
So it can combine some of those messages, right?
Exactly. Is that like, yeah, you've sort of thought of it in 2 seconds.
Yeah.
Perfect. And that would work really fine, except for those middle boxes. Because now we've changed what transmission control protocol is sending on the wire. And now your firewall middle box looks at it and it goes, well, what's that thing? It's trying to be a SYN packet, but it's sending me some data. Don't like the look of that. Seems a bit dodgy. Throws it away. Now you've developed a protocol that's maybe it's going to work for 90% of the internet or 80% of the internet, but it's going to die for the other 10 or 20%. This is the ossification problem. So we can't change how TCP is working, or we can't change what's going over the wire like that without risking things not getting there, things being mangled and misinterpreted by these middle boxes. Now, for a long, long time, getting back to this diagram, TCP has been the only game in town, and UDP is there, it does some important things, but the bulk of the work was TCP, and kind of rightly so, because it's got these nice features, the reliability, the congestion control, the flow control. The idea behind HTTP3 and Quic, so Quic, Quic, originally, I love this actually, originally stood for Quick UDP Internet Connection, but eventually the IETF standard decided it didn't stand for anything and it's just going to be Quic. So now it's Quic which definitely doesn't stand for anything. And that's going to do all this heavy lifting. That's going to sit above UDP, the horrible, useless, unreliable protocol. And it's going to look at those packets as they come in. And it's going to add some little data into the UDP packet. It's going to add some extra data so that we can determine, is it the same connection? Is this an acknowledgement? Has this packet been delivered successfully? Is there a missing packet here? This is where I'm torn between thinking this is a piece of brilliance and thinking this is so horrible I can't countenance it. About 12 years ago, I was sitting around chatting to some network people, and we had an idea. We wanted a new protocol, and we thought about this, and we sort of put the idea into the room. Maybe we could run it over UDP and then implement all of the reliability over that. And pretty much everybody went, that's too disgusting to contemplate. But actually, if you shed your prejudices, it makes quite a bit of sense. So now these things here, which usually live in the operating system, now if we're running things over UDP, what we're going to do here, so normally TCP would feed straight to HTTP. Here, we're going to put in a new thing at the application level. We're going to put in this Quic. The UDP packet has some extra information, and Quic is going to interpret that, and it's going to do everything that TCP would do. It's going to look for missing packets, it's going to send acknowledgements, it's going to do flow control, it's going to do congestion control. But because this is at the application layer, we're not changing anything about UDP. We've got loads of freedom to mess about here. The other thing we can do is we can add in that transport layer security. I've not left myself room in the diagram. We can add in TLS 1.3 in here as part of the Quic protocol. Now we've got ourselves a new protocol stack.
And of course, the middle boxes are it's just a standard UDP.
Yeah, for the middle boxes, this is just UDP. Oh, UDP, known it for years. To be fair, actually, some places they block UDP, but that's fine because you've got good old HTTP over TCP to fall back to. So what does the stack look like now? So our network, not changed. Really, if you want to change the network layer, which is what IPv6 is doing, be prepared to wait 20 years. The transport layer, so here's our old model where we have TCP going up to going up through TLS 1.2, going to HTTPS. So this is the transport layer, and then this HTTPS TLS 1.2 is our application. But now we've got this new option. We've got UDP, we've got Quic, which has TLS 1.3 doing the certificates and security inside it, and up at the top, HTTPS. And so really, philosophically now, this whole thing here, this is our transport layer, and we can specialize this for HTTPS. We can specialize it, so there's a problem called head of line blocking. I haven't really got time to get into, but it allows us, if a packet is lost, if a packet's lost in TCP, you've just got to wait. You can't send it to the application, you've just got to wait for more packets to come in. With UDP packets, you can read them as you get them. And Quic can say, oh, okay, I've lost a packet that's part of that image, but I've got a packet that's part of the web page, and I've got a packet that's part of the JavaScript, so I can assemble all them, and that image will show up at some point later. So we cured the head of line blocking, saved ourselves round trip times by amalgamating the TLS with the handshake. The whole thing, when it works really quickly. And we've got ourselves this transport layer that's specialized for a single application. TCP was an agnostic pipe that you shove data in at one end, get data out the other end, doesn't care what that data is. Quic specialized for HTTPS, really perfect for sending over web pages, but oh my goodness, it's muddled and horrible, and nobody, if you had a fresh, what we call a clean sheet design, nobody would have come up with this. So, is it beautiful? Is it ugly? It's efficient, it works, and it's going to take over the web. So, make your own judgment.
Get used to it.
Yeah, get used to it, absolutely. Get used to it, it's here. How much room it's got left. So now the sender knows, if I don't want to overwhelm that computer, I'm only going to send
know fairly well.
I'm only going to send 3 packets.
Let's just write a very silly little Python program. So I can write this function, let me make it a bit of bigger font size for you.